2 a.m. Glad that pleasure to be here and share with you this afternoon some of my research in aeronautics and space flight system, both in a aircraft community or space community, and also something that we could actually share with you, something going on in-house in Khalifa University. Okay, so at the event of current advancements on micro nano electronics, and especially in the advanced algorithms and high computational capacity, we are now uniquely empowered and enabled by these advancements. So we are actually beginning to address many long-standing challenges in aeronautics and the space flight research. So I would like to maybe take this opportunity to share with you two topics. One is in air vehicle related, the other is space vehicle related. And particularly air vehicle related, we're going to talking about, quote unquote, the digital air vehicle concepts, namely mission adaptive digital composite aerostructure technology that I personally involved in developing. And also like to, discuss about the future directions from my perspective, and followed by innovative future spaceflight technologies. Notably that now we have a number of CubeSat mission within KU, so something that we would like to explore further. And also planetary reentry vehicle, something that, for example, in the future we're going to go to Mars and building up the infrastructure there, and that will actually be the type of future research direction I think would be interesting to learn. So as far as a future advanced air vehicle concept is concerned, I think as you can see that we came in a long way from the first piloted aircraft back at the dawn of the 20th century to something that is ongoing, large transport aircraft that is really taking advantage of advanced avionics, composites, to something that we're actually expecting that coming in the future, such as urban air mobility, where everybody can fly. So these are the type of things that we thought would be the future that we would like to explore further, and really anticipating audience, students particularly, to join us. So when it comes to digital aerostructure concept, quite frankly, Boeing 737 is probably the most popular regional aircraft in US, and it's very complicated structures. It made of 2 million parts, and of the 2 million parts, there are 400,000 unique parts. Those unique parts, those 400,000 unique parts, implies that, unfortunately, we're going to be having a very special tooling for producing those parts, and then also related to that is very specific assembly process. So now what we're actually trying to address is that whether there's a way to actually do away from that kind of conventional wisdom. So the one thing that we've been looking into is that we would like to. Oh, I'm sorry. I think I was. So what we actually believe what we can do is that mimicking what is actually happening in the electronic industry. So what they're actually trying to demonstrate in electronic industry is that whether a collection of components can be rebuilt, to use a particular applications, functional units, or they can be, reassembled or for another applications. And as you can see, that if this can be shown, feasible, then the life cycle of any given component will actually way exceeds the conventionally engineered components. So these are the sort of area where we think that we can actually, really utilize our expertise in terms of building up the future sustainable systems. And this is sort of the idea of a digital construction in a nutshell. And in order to demonstrate the feasibility of the concept of a discrete construction of the discrete digital materials, I'm going to show you a number of examples that we actually worked on in the past. Something that we are actually still discussing now in KU is trying to continuation of that so that we can actually build something that is sustainable. So to just, as a first example, what we did was, come up with the digital wing concept, okay? So this is really, what you're seeing is that the highlight of what that we actually built. A pair of a digital composite wing. We started off from the laminated composite material, 24 inches by 48 inches. I'm sorry that I'm still using the British units. So we actually laid out the entire design of the airfoil, and then we utilized the water cutting to cut out the parts, and we hand assembled them, and then we went through the entire exercise of doing the wind tunnel testing, both at MIT tunnel and then also NASA wind tunnel. So of this wing that we are showing, which is a wingspan of about 1.3 meter, it consists of 106 parts. And of the 106 parts, there are only 7 unique parts. So by now you can see that the similarity that we're actually talking about is kind of a Lego approach. So those of you who actually play with a Lego, that that we have a bunch of Lego pieces, but all the pieces looks alike, but there are only a handful of them are unique, okay? So this is sort of a, engineering, more scientific approach of that concept. So as I said, that we actually have a 1 degree, I'm gonna play this video. You can see that we actually have a servo actuator that, passing through the wing, from the wing root to wing tip. What it does is that doing the 1 degree of a flip, the twist. So we actually use this twist to perform sort of ideal, rolling capabilities. So we actually did not only the wind tunnel testing. At the end, we actually built up the entire scale UAV model. We actually test flown the vehicle to perform a very interesting maneuver. Something that we thought that really implementing this discrete construction approach is really enabling that type of adaptability for the future air vehicle. So now what we've been asked to do is to demonstrate that, can your concept of this discrete construction scale up? Meaning, can you actually scale up beyond this 1.3 little UAV? So what we actually took up is to build up a larger scale, which is about 15 foot, which is about 5 meter wingspan, blended wing body, which is a lot more complicated. But the concept that we actually demonstrate, underneath the concept, is that we try to utilize the discrete construction with the digital material toolbox approach. What I am actually showing you here, there are 8 parts in the toolbox, actually, as you can see in the screen, okay? Those 2 volumetric pixel that I'm showing there is a 2-inch pitch, okay? So the two that I'm actually circling, and those are 2-inch pitch size, okay? And we coined them as Foxo, meaning it's a combination of 2 volumetric pixel is analog to the electronic pixel concept. So this Foxo will be the building block of building up the vehicle constructions. So what we did was one of the main goal was to demonstrate the effects of aeroelastic tailoring of the aerostructure stiffness property. And as you can see, those 2 Foxo, it may look exactly the same, geometry looks the same, but it actually have 2 different material property because it has two fractions of fiberglass content. So one is flexible than the other. And honestly, we can actually do various of those variations so that when you actually can build up the structure, it can actually build in the tailored, whatever the tailored structure property that you want. The most important thing is that all this is actually done using very highly reliable fabrication process. Well, of course, we also use a few parts that are actually been utilized in 3D printing. So this is actually showing you by utilizing the Foxo, we're actually building up with the help of a number of summer intern students to build up the wings. Okay, it takes about 6 days to build up entire wings, and half spanned, weighs about I would say 12, 13 kilograms. So it's something that at the end of the day you can actually hold it up. Okay, so it's very easy to hold up, but nonetheless I think the structure property is quite impressive. Something that we have been doing the wind tunnel testing utilizing the NASA facility. Okay, so the picture bottom right showed you the assembled part that is ready to ship out to the tunnel facility. Okay. I just thought to subsequently we have done a lot of wind tunnel testing at NASA Langley's 14 by 22 foot wind tunnel facility. We had excellent support there, as shown in this picture, which is a 5-meter wingspan. And one thing I would like to share with you is that the very last day of tunnel testing, I think after all the data being collected, we actually received a permission to go ahead and break the aircraft, okay, which was, everybody was excited about that. And we actually ramp up to 90 kilometer per hour, almost like a 90 meter, more than 90 kilometer per hour. But the wings actually, was still sustained. So the structural performance is quite impressive. Okay, so as you can see, the one obvious motivation for us in future direction is be able to. I think I have yeah. Is be able to automate the entire process. Okay, so the gantry system as shown here, the video actually shown here is a gantry system that automate the connection, because right up to this point we've been utilizing a lot of manual build-up. So I think this is the future, that artificial intelligence, deep learning, and incorporate into robotic manipulator. I think that's the direction to go in the future. But as you can see, the gantry system has a limit. We cannot scale up to the size of the vehicle, the structure that we actually built up. So in parallel, what we have done is that to introduce another concept, which is utilizing the relative robots, as you can see on the top right. So subsequently, this relative robot and the gantry system, I think they're going to be cooperating in actuality, so that in the future we're going to see the future digital aircraft factory, as is shown on the left, bottom left. Okay, and we believe that the stuff that we've actually been covering up to now is really something that we could demonstrate for the future vehicle concept, namely the urban air mobility. So there are a lot of effort, including the Uber, you name it. Hyundai is actually working on it. Toyota is actually supporting it, the effort. Joby has been hugely involved in this, building up the urban air mobility vehicle in the future. So I believe this is the future to go, and therefore this is where we can actually do interruption in terms of, do away from the conventional wisdom, completely different way of building up the aircraft. Okay, so I think the thing that the digital construction concept, the innovative in terms of a new way of building up the structure is something that we thought not only impacting the aeronautics but also impacting the future spaceflight systems. It's something that I would like to share with you here is that, as you know, that the many exciting space missions are underway. UAE has launched Mars Hope last July, and I think it's going to arrive sometime next month. So there are also many proposed lunar missions from US, China, and India, and so all of a sudden I think space exploration is actually attracting a significant public attention nowadays. And at home, in Khalifa University, we actually already launched 2 CubeSat missions, namely MySat-1 and the MESENSat. And there are 2 in the working to launch Light-1 and the DebiSat in the next few months. So, so there has been some continuous research, and also in the front of human habitat in Mars or on the lunar surface. It's something that we would like to, really like to explore and get students' anticipation and participation. So, so CubeSat, I think, is because of a small scale of its size, I think is ideal for exploring a lot of interesting space mission in the future, and something that we would like to continue to do utilizing the YASA Space Lab here in Khalifa University, which is supported by UAE Space Agency as well as YASA Communication, something that we would like to continue to support and do. And in terms of a large payload delivery future to Mars, for build up the human habitat there, and I think it is inevitable to enable some sort of flexible decelerator. Something that we can actually slow down, and then, before we do EDL, which is entry, descent, and landing. The one effort is Dr. Elena Fantino at Aerospace Engineering Department. I think she has been working on this area, and there seems like a good traction in that area as well. As far as the future direction goes, I think it is huge to actually build up a large structures in space, and the question is, how do you do it, and how quickly can you do it, how cheaply can you do it, and how reliably can you do it? So we felt that this is an area where we can actually really provide some impactful research and also some innovation there. So I would like to re-emphasize the fact that the human space habitat is one of the future directions that a lot of effort has been put into, something that we are continuing monitoring and focusing on. And the last, I would like to share with you some of the in-house activities that we've been currently launching. There are 4 projects within the KU Space Technology and Innovation Centers. I would like to share with you that, as you can take a look at that. Because of time, I think, and YASA also, YASA Space Laboratory has been really huge in providing the support for the DebiSat, upcoming DebiSat and Light-1. Okay, and without the undergraduate and graduate students' participations, particularly MSc Space Concentration Programs, graduate student from that, their participation has been crucial in a lot of this CubeSat development. I think my time is up, so if you have any questions, please, let me know. I would, I'm here to interact with you if you have any comments and interest. Okay. Okay. Rim, okay, thanks a lot, Rim. Appreciate it. Yeah, I think those of you who are interested in pursue some of the research area that I'm showing, that I showed here, both in Space Technology Innovation Center and the YASA Space Lab activities. I think feel free to reach out to me. I think you have a way to reach out to me, and we can discuss more. Okay. And there's the next questions. Low pressure, yes. Okay. Okay, KU combination, okay. Thank you, Muhammad Bashir. Since we're actually, for you to actually respond to any questions and whatnot, that I'd like to maybe have a few words about our ongoing activities in Space Technology Innovation Center at Khalifa University. We have 6U CubeSat, new 6U CubeSat we're going to be embarking on. That has, led by Dr. Viras and Dr. Lina. To actually demonstrate the microelectric thruster capability, to demonstrate whether we can actually do a on-orbit maneuver, and that's definitely one of the first within UAE to have that kind of missions. Really looking forward to it, and Dr. Abkasa and Dr. Khalid, they are leading the next generation antenna system. I think that's very interesting to see, very micro, small kind of a scale antenna system. And Dr. Daniel Choi has been critical in developing kind of a next generation space battery. All you can see that all this effort is, quite frankly, we would like to make sure that in the future that within Khalifa University we built up our own in-house sensor system and whatnot, so that we can actually showcasing those capability. And then also there are space rover activity that Dr. Lakmo, Dr. George, and Dr. Yaya has been leading. In a space rover on the lunar, in the future on the Mars rover. I think that's kind of something that hoping that we can actually track students' participations, and so that we can actually really build up not only prototype but also be able to fulfill the mission objectives. Okay, there are questions. Let me see. There are questions. Let me see. Working. I'm really interested in working on those topics. Okay, Mama Bashir, continue. Yeah, I think especially aerial and space robotics. Yeah, I think definitely aerial robotics, a combination. NASA, as you know, that NASA has developed launch, this Mars rover, but with Mars rover has, on board these helicopters that developed by JPL. Something that I think we should explore, because rover actually has limitation, meaning how fast it can go, how area it can cover, but you can actually combining that rover plus the helicopters or the flying vehicle. I think that would be a great combinations. What was the purpose of the wind tunnel testing? Oh yeah, the Rafid, the tunnel testing objective is trying to characterize because the airfoil, the airplane that we built is such a out of ordinary. Okay, so we just want to make sure whether it's actually behaving the same way as the conventional airfoil. Okay, because the airfoil that particularly that we're using is a NACA 012. So it's we know exactly how it behaves, and indeed the tunnel testing shows that is how it behaves. So it's on one hand is really good to see that indeed that we're building something that can behave as a conventional wisdom, but on the other hand we can actually utilize this 1 degree freedom twist on board. There's no external flaps, no nothing. I mean, we're just using the wing flap. The whole concept is to make it morphable. Okay, so one-dimensional twist we were able to do yawing and then a little bit of assisted pitching. So as you know, we usually rely on an elevator to help pitch up, but the CG is such that we have a small moment arm. So in fact, we can actually rotate both wings simultaneously, so they will actually provide some additional assistance in pitching moment. So that was, interesting additions that we observed. Thank you, Rafi. Yeah. Okay. And okay. I want to ask about the future for urban mobility. Isn't going to be affected due to current pandemic? How it affected the air navigation? Oh yeah, I think it's definitely. I think definitely this is going to impact it. the future urban air mobility is something going to be impacted by what's going on now in pandemics, of course. I mean, everything got impacted, not just urban air mobility, to say the least. But I think, believe it or not, the research is still ongoing. I mean, quite frankly, I'm also still continue working on that area. We published a couple of papers in that area already. So this is something that is ongoing. It's actually been slowing down a bit, unfortunately. But I think, if we actually open up the horizon, we are really seeing the future. I mean, like maybe 10 years from now, that we should be able to see a scale, a fleet of, urban air mobility vehicle is going to be flying around in particular designated area. Okay, I wouldn't be surprised. Okay, I wouldn't be surprised. Okay, so there's other. Can you please go back to the picture? So Rafiq, you asked me to go back to the picture. So yeah, let's see. You're talking about this picture, I believe. You're talking about this picture? Yeah, Dr. Rafiq, you're talking about this picture. Yeah, I don't see his response. Well, maybe he's thinking. Yeah. As you can see, the entire process, without help of capable students, we can do it. We cannot do it, and so we really need, students, graduate students, undergraduates, your participations. Okay, so I'm really calling on you, rely on you to participate in this kind of effort to build out the capability, because you are the future. Okay. So I think Rafid actually told me. Can you please go back to the picture? No, the wind tunnel test. Tunnel. Oh, tunnel. Okay. Ooh, tunnel. Okay. I think this. Yeah, I think you meant this guy. So in this case also, we actually did. I mean, because of time, I didn't actually go very deep into this, because, just talking about this may take up a couple of hours about talking about the detail. But nonetheless, at the get-go, what we're trying to do is that at one side of wing, we have one material property of a Foxo. Oh, by the way, the entire wingspan, which is about 5 meters, it consists of more than 5,000 Foxos. Okay, meaning that, and each and every one of those are connected by students. I mean, I'm really grateful for those students, their contributions. So on one side of a half span consists of one material property, and then the other side a different property. Number one. Okay. Number two is that we have again 1 degree of freedom actuations, meaning that from the ring root to the wingtip, we have a torque tube, so that we can actually twist it, the entire wingtip, okay, so that the entire structure can be twisted a bit. It doesn't take a whole lot, as you know. It doesn't take a whole lot to actually do like a couple of degrees of twisting already give you a huge rolling moment, capacity. And we saw that in the wind tunnel testing, and then we subsequently published a couple of papers, from that effort. I don't know whether this, Rafiq, did I answer your questions, but okay, yeah. Okay, I hope that I answered your questions. Okay, thank you very much for your time. Okay, thank you very much. Thank you.